This whole vape collection thing has got completely out of hand. Let's see if we can power a house of these things. A quick warning before we start, do not attempt to replicate anything I do in this video. It covers some pretty dangerous stuff. So these ridiculous disposable vapes have actually got fully rechargeable lithium-ion batteries inside of them. And these are the exact same batteries that we use in our phones and in our laptops. But these vapes have been designed to be thrown away after just a single use, which is just completely insane to me. So I've been on a bit of a mission to expose this by building a fully rechargeable power bank and e-bike battery out of them. And now I think I'm going to dial it up a couple of notches. So at their peak in the UK alone, over 1 million of these are being tossed away every single day. And while some places are finally banning them, in most of the world, this is still happening at a mind-boggling scale. So how about we find out how valuable these devices actually are? And can we use them to take this whole workshop, or maybe even my entire house, completely off grid? So if we wanted to build a massive Powerwall battery pack, how many vape cells would we need exactly? Well, to work this out, we need to wrap our head around battery capacities. So if we have a small cell and it's able to output a power of 1 watt for a whole hour before completely running out, then this means it has a capacity of 1 watt hour. And for reference, the capacity of a typical phone battery is about 10 watt hours. Well, I want to build a massive battery that's got a capacity of around 2,500 watt hours. And this should easily be able to power my workshop for multiple days, or even power my entire house for about 8 hours, because my house uses about 6,000 watt hours of electricity per day. So the average capacity of a small vape cell is 1.8 watt hours. So to make this thing, we'll need almost 1,400 of these. But the bigger vape cells are about 5 watt hours, so we could get away with only about 500 of them. So in case you've not seen my other videos, extracting these cells is actually mega simple. You just rip off the bottom, pull all the insides out, and cut or desolder the wires from the cell. Now I've just got to do this another couple hundred or 1,000 more times. You might be wondering, how on earth did I get so many littered vapes? Well, for the smaller projects, I collected them from streets and from festivals, but this would have literally taken me years to get enough for this project. But luckily for me, there were some vape shops that take empty customer returns, and they were more than happy for me to take them off their hands, especially as they have to pay out of their pocket to get them disposed. Okay, I'm already seeing a big problem here, and I've formed a pile of good and bad cells. You see, if a lithium cell ever gets discharged below 3 volts, then it becomes damaged and unusable. And as we can see here, that's the case for about half of these, so they've been discharged way below their minimum capacity. So what I think's happened is, obviously people use these until the battery is completely empty, but the circuitry inside here still keeps sipping away very, very slowly at the battery, and I reckon most of these have been collected way over a year ago. And any that are particularly old, I think the battery has just been drained to the point where we can't really recover it. And this is going to be quite an issue, because if you think that I'm having to throw away about half of these that I still have to crack open and test, that's going to be an awful lot of time wasted.
2 hours later.
Hang on, I'm pretty sure I might have found a solution. So obviously, if you puff on these vapes, if it has battery, it's going to vaporize, as is the case for this one. And if it's out of battery, then blinks and it tells you that I've not got any more battery. But I found that if it blinks, it means that the battery is still above 3 volts. And if you puff one that is not above 3 volts, nothing happens at all. So if I make a machine that can actually vape these vapes, then I can rapidly sort them into good and bad piles and then not waste my time harvesting possibly hundreds or maybe even 1,000 plus dead vapes. So luckily I've got a pump from a CPAP machine, and this has the same amount of air pressure as a human lung. So this should actually be perfect for something like this. Let's give it a go. Oh, look at that. There we go, them two working. And this one doesn't. So I should be able to just leave this running and sort through loads of vapes, put all the working ones in a good pile, put all the non-working ones in a bad pile, and we should have halved our workload really. Well, it certainly seems that the bigger ones withstand the test of time much better than the smaller vapes. And I guess it makes sense, because it's going to take much longer for the internal circuitry to slowly sip away the power of these bigger batteries. So there's been a recent disposable vape ban in the UK, which is absolutely fantastic news, and hopefully many other areas start to follow this trend. So the vapes now have to support replaceable pods and have a USB charging port, but it should have been like this from the start, given that USB-C ports cost about 3 cents. But I'm actually a bit skeptical as to how effective this will be, because I've noticed that shops stock way more of the complete kits than just the refillable pods, so people will eventually resort to buying a whole new vape because of the lack of availability of these pods, and the complete kits are about as cheap as the old disposables anyway. But anyway, we're certainly heading in the right direction. So once these cells are removed, we still need to test them to find out their actual capacity. And as we're going to be connecting a bunch of these cells together in parallel, it's really important that they're all charged at the exact same voltage level. And that's why I got 3 of these cell testers here, which will automatically charge them all to the exact same level, and will also measure their capacity so we can group together the cells with similar capacities. So this thing of course was made for 18650s, which means we're going to have a pretty hard time hooking up these tiny little vape cells. And in the e-bike build, we added some crocodile clips to the top, but these were just dangling everywhere and it kind of spooked me out because they could easily short circuit. So I think we can figure out a way better way so that we can just slot in the cells nice and easy. It's going to save us a bunch of time because we're going to be doing this for hundreds of these cells. So I reckon we can make some conductive spring things. If we 3D print some small cubes out of flexible TPU and then wrap it in copper tape, then these will be nice and conductive and can squish down to the size of the cell. There we go, these fit beautifully and make a nice solid connection. So now we can get 24 vape cells slotted in, charged and tested in bulk. Once the cell has been fully processed, I write down the capacity on the side of it so that I can then sort the cells into groups of similar capacities. And it's actually really important for the cells to have the same capacity when they're connected in parallel. I'm going to focus on just collecting the big ones now, because with the small cells, I'm lucky if I get half of their rated capacity, so I'd need like 2,000 of them. So focusing on the big cells is definitely the way to go. I really don't think this little montage does justice for how stupidly long this cell harvesting process has taken me. By this point, we're already genuinely about 2 months in since I started filming. I mean, it takes about 2 to 3 minutes to extract and desolder each cell, so multiply that by at least 600, and then it takes about 2 hours for each batch of cells to then be balance charged and tested. That's the problem with these vape recycling projects. The amount of labour needed is just absolutely massive, and also shows why recycling programs for these things is such an enormous challenge and barely even feasible most of the time. Okay, so we should have around 500 cells harvested now, but when building big projects like these, we always end up needing a bunch of custom parts, whether it's PCBs, 3D prints, or mechanical parts for example, and finding a reliable place to get them all can be a right headache, which is where JLC PCB comes in, as they offer a true one-stop manufacturing service. So previously I've ordered custom PCBs from them, like in the vape battery power bank video, and this time I've used their 3D printing service to make a bunch of modules to hold all the vape cells together. Plus I grabbed a ton of extrusion from their mechanical parts store. Everything came out great, the quality solid, price is super affordable, and it's honestly saved me a lot of time on this build. They also do CNC machining and full PCBA assembly, so if you're looking for a reliable one-stop manufacturer for your next project, definitely check out JLC PCB. The link's right below the video. Right, so now we've got about 500 of these all extracted and tested. So now we need a solid plan of how we're going to combine them and construct this thing. So to make my life easier and make this thing nice and modular, I'm going to use a 3D print to bundle 9 of the cells together in parallel. This will add up their capacities, so we'll form some low voltage, high capacity modules. We can then group a few of these modules together again in parallel to make an even bigger capacity parallel group of cells. Then we'll need to increase the battery voltage, which is done by making lots of these groups and connecting them in series to then add up their voltages. So I'll stack up 14 of them in series to give us a total voltage of around 50 volts. And there we go, we should have a massive high voltage, high capacity battery pack ready to go. So this thing's going to be pretty enormous, so I think I'm going to build it in 2 halves and then we can connect them together later on.
Alright, so building this thing is going to take bloody ages. So that's why I've recruited some extra help from my friend Max, and he's actually the same guy that's been designing all the 3D prints for the past projects, and even these little cell holders. So yeah, let's get started.
Let's have a quick look at how we're going to build these things. So we want to be connecting all these 9 cells within each module together in parallel. And that's why on the negative side, we've just got them all hooked up together using these bus bars. But then on the positive side, usually you would have all the positives linked together and you'd call it a day. But because this thing is going to be powering a literal house and could be drawing a lot of energy and also running for long periods of time, I want to add some extra safety in there. So instead of directly connecting all of the positive sides together using the copper strip, we solder a fuse between each cell and the copper strip, meaning every single cell in the pack will be protected against short circuits. And this idea is kind of semi-inspired by this big old battery pack over here. And yes, I do have way too much lithium in my workshop, but this is a battery pack from a Tesla Model X. And if we look closely, we can see the individual cells here, and they're connected to the bus bars via these tiny little wires. and these wires double up as tiny little fuses. So yeah, if any of the cells are working too hard or have an internal short, these little fuses are going to pop, disconnecting it, and everything else should remain pretty safe. So it's just a case of slotting in the cells, putting down some heat resistant tape to protect the 3D print, cutting some copper strips for the bus bars, soldering fuses between the positive sides of the cells and the bus bars, flipping it over, and soldering all the negative sides together via more bus bars. So only got to do this, what, another 50 something more times?
So we got the first few modules created, and not gonna lie, it looks really quite dodgy. It looks like a... Yeah, it really does.
Here we are, we've got 50 something modules finally built, and this should be enough to bundle them together and form 14 parallel rows. Right, so obviously these modules are going to need to be connected together to form the final parallel rows of the power wall. To get them all mounted up, we insert these 3D printed holders into each module, which will let us clip them onto some aluminium extrusion. Then we bolt them down so that they're properly locked in place. Yep, these things aren't going anywhere. And then for even more soldering to get these modules finally connected together in parallel. So again, I'm just using more copper strip here to link up these things, and I'm trying my best not to melt the 3D prints too much. Then I flip it over to connect up all the negative sides, and there we go. We've got a row of 36 cells all in parallel now. Then to finish it off, I put some silicone around the cells just to make sure that they're held in there properly. And once again, I need to repeat this a bunch more times, 13 to be exact. You know, I'm starting to think this project might not be too good for me, given all the solder fumes and residual vape liquid. Yeah, the workshop certainly has a weird smell to it. Alright, we're getting pretty close now. So we've got all 14 parallel rows created. And I tell you what, these things are looking way cooler than I thought they would do. So we've just got one more thing to figure out before we can finally build a frame for this thing and get it mounted on the wall. And that is, how are we going to hook all these up in series? But I've not really made a nice easy way to actually connect these together, because we're going to have to connect the positives of one row to the negatives of the next, and the positives to the negatives, and so on. So what I'm thinking of doing is adding a bunch of wires to both the positive and the negative side with these little clips on them, so that hopefully when they're all stacked up nice and close to each other, I can just clip the positives of one side into the negatives of the one above it, and we just repeat that until hopefully they're all connected together in series and we get a nice high voltage. These wire clip things are called Wagos, and they're going to make my life so much easier, because I really don't fancy sticking a soldering iron in the middle of a live battery pack while we're connecting it all up in series. And then here I'm using some Kapton tape to insulate the tops and the bottoms of the cell. This is actually super important because some stray metal could easily accidentally short out some of the inside of the battery pack and start fires. Realistically, this tape isn't quite enough, and I'll add some more insulation later, but I think it'll do for now. Right, one half assembled, and this thing is pretty bloody heavy. I mean, I don't know what I expected, seeing as there's literally hundreds of cells here, but yeah, that does weigh more than I thought. I tell you what, using aluminium extrusion is absolutely perfect for projects like these. Everything just bolts together dead easy, and it is mega strong. Right, the frame is constructed, and this thing is an absolute unit. So now we need to get these cells finally connected in series. As we explained earlier, it really is just as simple as clipping the positives from one row into the negatives of the next using these little connectors. So just like that. There we go, that's one connection done. Just got 4 of them to do on each side for each module. Let's just take a quick minute to appreciate how dodgy and dangerous this is, especially with all the wires and stuff hanging out. Yeah, I am paying very close attention to what I do right now, and I definitely do not recommend anyone ever builds a battery pack like this. So now we've hooked up each half in series, we can measure the voltage across each half to make sure it's around what we would expect. There we go, 25 volts on this half. That's looking pretty good. And another 25 volts on this half. So that's fantastic really, it tells us that everything is perfectly as it should be. So now we've just got to connect both of these halves together. So we're going to connect them at the bottom, and then this is going to be our negative, and this side is going to be our positive. So we'll just have our connector up here. Now let's get on to how we're going to link up these two halves. So we could use the clips to make a direct connection between the two halves, therefore putting them both in series. But we could also kill two birds with one stone by linking them together with a big chunky fuse. You see, if something goes wrong and we draw too much power from the battery, the fuse will pop, disconnecting this link between them and not allowing any more power draw. But by having a fuse in the middle, it means that even if there's a fault on the inside of the battery, where the two halves internally short together, then the fuse will also pop and save the day. So I'm definitely going to do this. And there we go. Just like that, we've got 50 volts. Absolutely spot on. And finally, it is mega important that any battery pack has a battery management system, or BMS. This will monitor each parallel row of cells and make sure everything's healthy. If you don't do this, then there's a good chance that it'll explode, as I've seen in the past. To wire up the BMS, you have to connect a wire to each of the parallel rows so that the BMS can monitor each row's voltage. Fortunately, I've already got a huge BMS from the 50 mph mobility scooter video. So let's get that moved over. I've added a bunch of clips to the series connections that take in 3 wires, which means that we can just clip in all of the wires from the BMS. And then finally, we add a big fat 200 amp connector to the top. Right, battery management system is all completely hooked up now, and I've doubled and triple checked all the connections, and it does look fine. So hopefully we're not going to be releasing any magic smoke, but there's only one way to find out. So if I hold this button, I think they are good beeps. Let's see what's coming out of this thing. Look at that, 50 volts. Yeah, this thing is completely working. Battery management system's happy. I think we're ready to start connecting this thing to the workshop. Now, unfortunately, our battery pack puts out around 50 volts DC, and you can't power any mains household appliances with this. For that, you need a voltage output of around 240 volts AC. So what we're going to need is a thing called an inverter to convert between these two voltages. Like this one, for example. So my house gets its power from the grid, which then also feeds power to the workshop. But we can disconnect the workshop from the house and use the battery pack and inverter to then power the workshop. Theoretically, we could also disconnect the house from the grid and then feed power from the inverter into the house as well, which means everything will be completely off grid. Alright, so we've got the battery all connected to the inverter, and the inverter should be hooked up to the workshop now. So inside this box, we can see that we're getting power from the house at the moment. So if I turn this off, there we go, no power, very spooky. And then here, this is the circuit breaker for the inverter. So let's turn that on. Right, now if we switch on the power of this thing, there we go. Now we'll just have to give it a few seconds to boot up. Right, so we can see we've got 49.2 on the input and 229 on the output. This is what we want to see. So theoretically, if I turn this, oh, look at that. This workshop is now being completely powered 100% from these vape cells. This is crazy. Alright, there we go, got the oscilloscope going. Got my extractor fan, power supplies, everything. All of this powered 100% by disposable vape batteries that would otherwise be in the landfill most likely. So we can see on the BMS app that yeah, we're drawing about 200 watts from the battery. And here we go, the inverter, yep, 200 watts of power draw. This is just amazing, isn't it? Okay, now for the test we're all waiting for. Can we actually feed power back into the house? So we're in the house now, and I've turned off a big switch outside, and we've turned off the main switch here. So we have absolutely no power at the moment. Nothing. Alright, so we're back in the workshop. We've got the inverter all powered again. So if you flip this, okay, that's what we expect. That's power going to the workshop. Now if we flip this, oh, the fan's kicked in, it's certainly working harder. Let's go and take a look. Check this out, so we're still completely off grid here, main switch is off, and the microwave is absolutely happy. Got lights working. Let's see what else is working out here. Yep, extractor fan's all good. And I tell you what, I bet we can even make ourselves a brew. Yep, there we go. Working absolutely perfectly. So to answer the question, can you power a whole house using just disposable vape cells that are thrown away in the millions? Then yes, you absolutely can. Right, and check this out. I can even edit this exact video using the power of disposable vapes. I fully cannot wrap my head around this. So there we have it. At the moment, I can charge the battery pack from the grid at night when electricity prices are nice and cheap, but I bet we could easily whack some solar panels on the workshop and go entirely off grid. So let me know if that's something you'd want to see. If you enjoyed watching this video, then drop it a like to help the algorithm and also spread some awareness of this ridiculous source of e-waste. See you in the next one.